All right, we're live.
Shall we get started then? Okay. All right. Hi, everyone. My name is Ray. I'm a first year at Harvard and a helper for this HMMT education event, and we are so excited that you all are joining us tonight. Before we begin, I would like to share some reminders and rules out of our respect for our speaker and those attending. Feel free to use the Q&A feature to ask any questions and upload questions you like. However, please remember that Professor Lowe is taking time out of this very busy day to speak to us all, which we're very grateful for. So please be respectful to Professor Lowe and your fellow attendees. HMMT reserves the right to remove you if you do not use the chat and Q&A functions appropriately. Tonight, we will be hearing from Professor Po-Shen Lowe, the one and only. For those of you who are not familiar with our speaker, Po-Shen Lowe currently serves as a professor of mathematics at Carnegie Mellon University and is a coach of the US IMO team. In his free time, outside of his research, teaching, and outreach activities, Professor Lowe has founded XP.com, numerous free online learning resources, fights the COVID pandemic with a novel tool, Novid. Professor Lowe is essentially a superhero. Today, Professor Lowe will be sharing his talk titled Applied Pure Math, which draws on his journey using mathematics to create Novid. With that, thank you again for joining us, Professor Lowe. The floor is all yours.
Wow, well, thank you. And thanks to everyone for coming. I have to say, I mean, I'm not a really picky person on intros or anything. You guys are too generous. And also, actually, I really enjoy coming to these events. Look, if the world was back to normal, I would be in Boston right now with all of you, because that's actually what I like to do on the weekends, to go and visit places where lots of interesting people gather to talk about mathematics and other things. Maybe I do want to emphasize, though, one of the reasons that I always want to give these kinds of talks or interact with all of you is because I'm selfish, okay? I'm going to get old at some point, and I'm going to need you guys to go and save the world. I'm serious. I mean, at some point, what? If 20 years from now, there's another major disaster, you think I'm going to be able to do anything? I won't be the right person. I won't even know what's the latest newfangled technology. We need you guys. So my real selfish hope is that somehow by running around the whole country and talking to all of these people who are future potential leaders and all kinds of things, maybe you'll get some crazy ideas too. And if you get some crazy ideas, you'll save my life. So thanks in advance. So anyway, so that's also, somebody asked me actually just yesterday. That person asked me, what do you like so much about coaching the US IMO team? My answer was very simple. It's that, well, it's really fun to be around people who are just smarter than me. Okay, it makes me feel better and more optimistic about the future. And the best way to find that is just work with these very, very talented people like all of yourselves. Okay. Now, my story that I want to share a little bit today is I titled this Applied Pure Mathematics. I actually stole that idea of the title from a colleague of mine. I have a friend who's also a math professor at Carnegie Mellon. And there was some point, maybe a few years ago, when we were hiring the new dean. The dean is the person who oversees multiple departments: math, biology, chemistry, and physics. And as we were interviewing this person, we all went around the room explaining what we did. And, here was a biologist explaining that they were working on curing cancer. Here was a chemist saying that they were working on polymers and understanding how to, I guess, make stuff. And then I got to my colleague, the other guy in my department, and he cheekily said, I'm a theoretical applied mathematician. That means I like to work on applied math, but I like to think about the theory behind why all those things are true. I like to prove the theorems and write the papers. When I heard that, I said, oh. Well, it got to me and I said, oh, I'm actually an applied theoretical mathematician. What that means is I like to think about any kinds of interesting breakthroughs that you can make with hardcore mathematics, but actually go and use them somehow in the real world where it just gets dirty. And you don't necessarily write research papers out of that, but you make stuff. So that's what I've always enjoyed, actually. I'm a pretty practical person. And my story is, I started off as a math contest person, and then I went to college. I studied mathematics, but just to put some color around the life, just like how you see all the people who are organizing this, they didn't just go to college to take classes and just do the college stuff. They did other interesting things as well. And one of the most interesting things you can do in college is to learn how to do real stuff, which is, putting on a tournament like this. I'm sure they had a pretty intense day or maybe a pretty intense last night. I don't know how many of you slept last night. Usually the way this thing works is whenever you do something for real, you find out that everything just kind of breaks at the wrong times. Oh, maybe I shouldn't say that. Maybe you guys are perfect, okay? But whenever I do something, things just break at all the wrong times. But in any case, I encourage, like, whenever you guys go and do your college experiences, go and learn other stuff too. I definitely did. I spent my college experience doing a lot of random stuff with computers. Now, I then went on and did like math professor stuff. But when I did math professor stuff, I was always thinking, is there something I can use all of these things for? And that's how I founded this XP. I learned how to be a social entrepreneur. I learned how to build a team. And these are all things that I'm just going to share. If you try to build a team to do something, the first time it's not going to work that well, unless you're just like super genius or super lucky or have great like people skills. And I've done this a couple of times, and every time I do this, I get a bit better, which is what helped me to somehow be in the right place at the right time on Pi Day last year. So I remember Pi Day because everyone in this room would remember March 14th if that was the day that something happened. And I know what happened to me on Pi Day last year. I got an email from a very, very respected individual from the Hertz Foundation, associated with the Hertz Foundation. Actually, I'm going to talk about the Hertz Foundation because the people who are on this webinar are people who might actually apply for a Hertz Foundation fellowship someday. The Hertz Foundation was created about half a century ago, and John Hertz was the person who provided the resources. Hertz is the same Hertz as rental car company, not this 1/seconds. That's a different guy. But this was John Hertz, the rental car company guy. He made a lot of money. Well, made a decent amount of money. Actually, just like fun fact, he made his money not just on rental cars. He actually also like invented the notion of a taxi service in Chicago. That's actually why the Hertz logo is yellow, in case you didn't know. It's yellow because he was doing yellow cab in Chicago. Now, that's like fun facts, okay? But other fun facts about this Hertz guy, he was like very few relationships away, very close to the people who were in the Manhattan Project. Again, this was half a century ago. And for example, he knew Edward Teller, who's the father of the hydrogen bomb. Not really something you might want to be the father of. But in any case, well, I shouldn't say that. At the time, it was important. But in any case, there were all of these different relationships. Yeah, I really shouldn't say that. Actually, it's very hard to go and make these kinds of judgments. I will not make that judgment. However, because of the relationship back half a century ago, it was thought that we might need to have an army of scientists that someday, if you needed to, you could bring back together to make another Manhattan Project. And so the Hertz Foundation Fellowship is something which they go and do interviews to find about 15 people every year who are about to start their PhDs, who have broad skills in the sense that if you someday were working on some big global project, you wouldn't only know your skill set, but you'd know a lot of other things. If you pass all of these interviews, then they offer you funding for your PhD with a catch. The catch is a moral commitment that if there's ever a moment of national emergency, you'll go to help. I'm one of these people. And when I signed on, I remember thinking, because we were in the 2004 group, we remember thinking it wasn't really like we're going to make more bombs. The world doesn't need more bombs. We actually kind of joked it'll probably be some biological attack that we get rallied to do something about. Well, Pi Day last year. So a message comes in from a really, really famous guy, actually. And it said, this COVID thing, it's bad. By the way, at that time, I was one of those guys running around saying, this is like the flu. Well, but it'll just be over soon. But this message came in and it was like, it's bad. It's actually something that can infect people and kill people who aren't just elderly. And long thing at the end, it was like, look, if there was ever a moment of national emergency, this is an international emergency. Anyone who has ideas of what to do, see if you can jump in. So I started thinking, what can I do? I'm useless. I'm a mathematician. What are we going to do? Like maybe I'll model something so I can tell you afterwards, like how many people died, or maybe predict something and no one will listen to me anyway. So I didn't know. But the next day, I happened to be reading the PhD thesis of my student. I had a student who was graduating. He gave me part of his PhD thesis. I was supposed to give him feedback. But I only read the first sentence because I suddenly realized after reading the first sentence, my gosh, we work on graph theory. You can use graph theory to fight a pandemic. Because we have smartphones now. So this is what was flying through my brain. I was like, oh, we have smartphones. With the smartphones this year, like unlike the previous SARS, this year, we could actually anonymously collect a big network, a big graph of which devices are interacting with which devices. You could combine graph theory and biological signals for the first time in human history and use this to stop a pandemic. So then I quickly went to Google to be like, can I actually go and write this thing? Do we have enough function calls? Are there enough phones with this thing? An hour later, I was like, it's possible. And it's going to be easy. We'll be done in a week. So I said, we're going to do this. The notion that you'll be done in a week is very important, because if I had known that I'd still be working on it practically 1 year later, I might not have gotten started. Well, that's not clear. It was an important enough problem. I probably would still have gotten started. But the idea that we can do this, then I just dove in. Unfortunately, I didn't read any more than the first sentence of my PhD student's thesis. But fortunately, he's a super genius, and he graduated anyway. And no students were harmed in the procedure of creating this. But as we started working on this thing, right, it was like the beginning was just, this is how mathematicians solve problems. You've spent all day solving problems. And you're like, what kind of tools do I have that I can start to pull together? I was just like, smartphones, graph, biological signals should be able to do something. And after hammering on this thing and doing problem solving for months, I'm happy to share that we accidentally discovered a fundamentally new way to fight disease, which is actually kind of a shocking statement to make from a pure mathematician, but that's why I'm an applied pure mathematician. And in particular, let me say a little bit about how this works. Okay, we're going to go into Q&A real soon, but I just wanted to show you this story of how it starts from a mission. It starts from a goal that we have to do something good for society, and it also starts from this germ of an idea that there's a new power that has not been ever tapped in human history. Can we figure out how to do it? Okay, and now, what is the idea? The idea is simple, okay? The way that normally people fight disease is they go and say, hey, here's somebody who's sick. Wait, why am I just gesturing in the air? So I fortunately, I'm calling you from my studio. And if I'm calling you from my studio, I have the power to draw stuff. And so I will subject you to seeing drawn stuff. But that makes it a lot easier for me just to do things. I don't have to wave in the air, right? So what we have is, normally, if you have a sick person, right? That's a sick person. If you normally have a sick person, the way that normally people try to control a disease is you go and find out, like, who else was around this sick person. That person appears to have 3 legs. That's not good. Anyway, you find out who else is around this sick person, and then you attempt to like remove all these people from society against their will. Okay, you attempt to go and grab all these people and get rid of them. And the key thing here is it is against their incentive. Does that make sense? The main thing is the way that you normally control a disease is you go and say, all right, got sick person, here are the people around them. Everyone, please go stay at home because you're a potential danger to society. And that's the premise of every zombie movie in the world. Because unfortunately, when you do things that are against people's incentives, people are really smart. And once they're smart, they find ways to cheat, and then you got a big problem. So we said, no, here, new idea. Very simple, okay? Simple idea is you got sick person. Oops, I accidentally pressed the button that lifts my pen. Sick person, okay? And now what I'm going to do is I'm going to draw like a bunch of other people. Yes, okay, these people are all like spending time in some way with each other. Nobody said that the graph was planar. Sorry, that was maybe a bit more technical term that I need to use here. But somehow, actually, it's still a planar graph. I could do it around the other way. But what you do is, like, suppose this is you. This is you. Our idea was actually very simple. Tell everybody the graph theoretic distance between them and the sick person. What's the graph theoretic distance? It is the number of hops. So, for example, this is 3 away from you. Does that make sense? The notion is just somehow if there's a sick person, the sick person is 3 steps away from you in this graph. What's an edge in the graph? An edge means that these 2 people have phones where the phones spent enough time close enough to each other. Those are just details, parameters that can be changed later. So if you look at what we've done, it was a very simple change, okay? Before, it was that you tell a Boolean. Boolean is a true-false value. Before, like all of human history was, got sick person, tell other people, were they or were they not neighbors in this graph? I'm using graph theoretic language. Our idea was simple. Every sick person, tell everybody else an integer. Go from a Boolean to an integer. If you do computer programming, when you go from a Boolean to an integer, you get a lot more data, a lot more information. And then once you're reporting these integers, which is like everybody who's sick, there's an integer of how far away it is from you. Well, then you can start to make like a little chart that looks like this. So what you see here is this is like something that we could play on an app, which just tells you here is how many sick people there are at various distances from you. And the way to read this chart is that the height of the bar is how many sick people there are. And this degree of the connection, that's the graph theoretic distance, which is just how many steps away that person is from you. And when we were doing this, actually, originally when we did this, it was purely for eye candy. It was like, we have a graph. Let's go and compute on the graph. Ooh, it's an algorithm problem. It's actually a hard algorithm problem because you might have a lot of vertices in the graph. Thankfully, we have some smart people working with us, such as a student from MIT, Brandon Wang, if you know him. He's one of the guys who was involved early on who helped to make these algorithms. Of course, he and I both have backgrounds that are both in mathematics and also in these like informatics types of competitions. And so actually, when we made this, we were just like, cool problem. Let's make it. Let's put it on the screen. It's nifty. It moves. Neat. As you can see, the date's June, right? We made it in June last year. And then we put it there. And a few months later, it was just like always on the screen. And a few months later, it occurred to us, hang on a second. This is huge. We are staring at right now, you're all staring at the first tool in the history of human civilization that you can use to avoid a disease before it gets to you on your network. This is preemptive. This actually changes the game from find people when they are already potentially infected after they're exposed, remove them from society against their will, change it to let everybody before they're exposed see something coming so they can defend themselves. Wait a second, what happens to the incentives? They flip. Suddenly it's not against your will. If you saw something coming, if you didn't want to get sick, you could use it. Actually, I can tell you what has happened. This is being used at some universities. There was some student at one of the universities who wrote to me about 3 weeks ago now. And he said, Novid saved my life. The app is called Novid. He said, Novid saved my life. I said, what do you mean? He said, well, my radar showed me that there was a case at 2 away from me. I was going to hang out with my friend. My friend had a case at 1 away from him. So we didn't hang out. As you know, it's very hard to eat lunch with a mask on. Right? And so the point is, what does this do? This actually just gives you a way that if you saw something coming, very small elective decisions can be used to go and protect yourself. And that's actually why I'm working on this now. So when I realized this, I said, oh my gosh, we're not just making some app anymore. The app is cool. If people use our app, great. But what I will dedicate a significant amount, like all of my energy on at this point forward is we have uncovered a categorically new way for humans to avoid disease. This could permanently change the course of how human civilization avoids every future pandemic. My job now is to get this idea as widely known as possible. And just like things are working out in the sense that earlier, like last month, I was giving talks about this at Stanford and at Georgia Tech and at the Chan Zuckerberg BioHub. People are noticing that there is this categorically new way of avoiding disease, which actually aligns all of the human incentives. Effectively, what this is it relays at long distances anonymously information about danger. Similarly, by the way, to how your human body, our human body has all these cells in it, and somehow the cells don't have brains. But somehow there are signals being transmitted at long distances within our bodies, which somehow allow cohesive action to take place. What I've just showed you is an automatic system that allows the entire human race of people to relay these kinds of informations in a way where everyone actually has aligned incentives. Some people say things like, oh, wait, but won't people not want people to spy on them? Well, it helps that we're not actually trying to spy on anyone. But the second thing is we didn't collect any information about names, addresses, phone numbers, or anything. And what we actually found out is that people, normal people, once they realize that they can see threats coming from far away and potentially help them, they actually want to use these things because they actually use all kinds of other things anyway that spy on them, like Zoom. Hi. It's just like we're using all these kinds of things anyway. And what we realize is like, oh, it's just game theory. If you align the game theoretic incentives, then the person says, oh, well, it gives me something that's really valuable. Am I willing to take the risk that they're going to somehow have this big network? Well, everyone else in the tech industry has that big network anyway. So in this case, then the decision goes through. So anyway, I've scratched the tip of the surface with what I'm working on now. The interesting things that I've been playing with now are basically using this pure math, graph theory, game theory, and actually a whole lot of other stuff in order to make the app. There was like number theory. For the first time in my life, I used the freshman stream, x plus y squared. If you do everything in a characteristic 2 field, or if you don't know what that means, like think about things mod 2, then somehow you don't have the cross terms. Anyway, so like all these like crazy things for math, I ended up using Fourier analysis because for part of what we do, our phones measure distances between each other using ultrasound. We basically built a sonar system. In order to do that, you sort of have to understand how math works. But if you can see, at the heart of all of this innovation was actually math. And it's also kind of funny, like the thing I've showed you is now completely obvious. It's like most people who see it are like, oh yeah, yeah, that makes sense. And then the next question that goes through many people's minds, many scientific people's minds is, my goodness, how come nobody else ever thought of this? It's just like totally obvious. But how come nobody thought of this? I've given like so many talks, talked to so many professionals. This is a new idea. Why? It's because of the math. It's because if you understand the graph theory like a native, then this is like what you would come up with. This is like exactly what a graph theorist would come up with if you think about it, which is how we actually came up with it. But this is also sort of revealing the value of, I hope that all of you who are watching decide to not only do math. I think that math is great. Obviously, I wouldn't have been able to get this far without all of that crazy math. But it's really important, I think, to also develop a lot of skills in other areas. Because who knows, if you actually need to do something someday, you might need to have cross-disciplinary skills. And so that's actually what ended up getting here. In some sense, I never actually learned applied math. I just learned a lot of pure subjects, like pure math, pure biology, pure physics, pure computer programming. And I just apply them because I'm interested. So that's like, I guess that's this part of the talk. I'd rather go into like a Q&A discussion. And what I mean by Q&A discussion is I can just go off on crazy tangents. I have approximately 40 minutes before I have to run off and give another talk. But what do we have? I'm happy to go off on crazy tangents now.
Okay, thank you very much, Professor Po-Shen for that amazing talk. So maybe the first question is, your talk is very much about Novid. What are the next steps for Novid, and how do you plan on getting more people onto Novid?
So again, remember my main thing, once I realized that we had invented a categorically new way for human civilization to fight disease, I was like, oh my gosh, I have to work on that because that is the biggest contribution I can make to humankind. So notice that's not the same as make everyone use Novid. These are different goals. If I was just a business guy, I'd be like, forget about that. Let's just go get people to use Novid. Instead, I'm a scientist. And maybe I'll also share a little bit to you of how I optimize, what I optimize for in my life. I don't optimize for dollars. I'm not actually trying to get rich. What I optimize for is a score, which is like how many people for how many years after I'm not on Earth anymore remember and appreciate something I contributed to. That's actually what I always cared about. Although last year, after accidentally finding some other way to solve quadratic equations, I realized that I already got that because now that's going into all these algebra books. So my score now actually is not bad because now like that's actually part of what everyone's going to be learning as they learn how to solve quadratic equations. Yes, it's totally trivial to everyone here. It's totally trivial. But for some reason, looking at the problem in a different way, it was useful. So then I changed the way I score. The way I score now is like how many minutes of everyone's life forever do I get to change, right? So that one gives me half an hour. Like everyone's going to learn algebra at some point. So I can help everyone for half an hour for like the rest of civilization. But like, how do I make more than half an hour? Well, then once I realized this thing about the disease, I was like, oh, that could boost your score into like a few hours now. So then, like, what are we trying to do with Novid? Actually, the main thing with Novid isn't to like play the political game of trying to get all these people to use it. Rather, I'm running the scientific line, which is I'm trying to talk to more and more people who are epidemiologists, public health experts, and so on. Some of them are working with us on actual deployments. And the other thing is actually, if you go to school, one place that we are trying to get more deployments is schools. Why? Because every place that starts using this is giving more and more and more evidence among the scientific community that's helping to analyze this, more and more evidence that this actually is how you should fight a pandemic. I mean, just like to stretch one more level, you see, for COVID, this is quite useful, but I'll tell you it's going to be really useful when airborne Ebola strikes. Airborne Ebola will happen at some point, possibly, and that will be bad because you know what happens when you die of Ebola? You bleed out of your eyeballs. That's horrible. Like, bleed out of your eyes. It's horrible. I'm saying like there's a spectrum of diseases which are gruesome. And while people hate death, they hate torture even more. And so what I'm trying to say is like, if you had a tool like this and you have a gruesome death when you get infected by the disease, my gosh, this is going to be amazing. The disease is just going to end. because everyone who sees the radar like 5 away is like, bye-bye, I'm staying at home. I don't want any of this nonsense. And what happens to the disease? Like, that's why I'm doing all of this. Because otherwise, if we don't get like everyone to know this exists, when that happens, people will be like, oh, I don't know, what do? We try everything we've done last time. I already know one thing, doesn't work very well. And then now, like, okay, practically other things with Novid, right? We are actually also, I also don't want to oversimplify. Of course, like, I'm being like provocative on purpose to say some of these statements. I'm not saying this would immediately destroy a disease. That's not actually responsible. But it's a powerful tool that was never there before. But then back to this other thing about, what are we trying to do right now? Well, actually, we are also trying to help people. And so one of the ways that we can actually grow this is we're trying to find out if schools or universities or cities are interested in working with us to try to make, the radar available for their regions. And so, I'm giving this talk here. If you go to a school and your school is trying to figure out how to reopen, if you get in touch with us, we'd be very happy to try to talk to your school as well.
So another I think one participant had a question about if you don't collect data, how do you see who to avoid when you, I guess, see something coming?
So there's a privacy issue. We live in a country here where people would not want to be able to be found out that it is them, right? So the way that I explain this is, here's what I would do. Because I'm also a professor, I might have to teach a class in person. At some point, I was actually told I was teaching a class in person. And I just asked everyone who was talking to me about the class, please install this app. It was not because I was trying to promote the app. It was for self-defense. Because here's what I was planning to do as a teacher. If I see red radar blip close to me, when I show up for class, I don't wear a cloth mask. Cloth mask does not really protect me that much. I will go and get one of these surgical masks, put it underneath the cloth mask, or I'll get an N95. Basically, what I'm saying is, even without knowing who it's coming from, because you can't, that's a privacy issue, it's still useful because you can just still go about your business, but with one of these like higher levels of protection that you normally wouldn't allocate the resource to because it's like one-time use. You know what I mean? Like one of those one-time use masks. I have like bullets, I've limited ammunition, but I can machine wash the cloth mask as many times as I want. Unlimited ammunition, whatever that means. So it's like, where do I deploy my tools?
And I think another question was, how much do you think Novid needs to be distributed in order for it, I guess, in order for it to be even more affected on some like exponential scale?
Yeah, so this is actually where the random graph theory came in. So actually, a lot of people didn't dare to go and make these kinds of tools, in part because they weren't sure whether you'd get enough people to use them. And if you don't have enough people using it, then, well, I guess it's not useful. But here's what we knew would happen. Let me just flip over to here. So this is just a web browser, which has a link to, not a link, it's Georgia Tech. The reason is because for privacy, we don't share any data that's like collected from the app publicly. That would be irresponsible. Instead, what we do is we look for Reddit posts because we figure that if someone posts on Reddit, it's public, right? So this is like some random student from Georgia Tech. And the interesting thing is they said this, the charts are unbelievable. What do they mean? Let's go look at a chart. Here's a chart. So they saw this. I'm going to zoom in. They saw that there were 1,000 people connected to them. And this is exactly what they saw. It was basically 2 weeks after they had told people, hey, let's use this app. And 1,000 people were connected to them. And this student was like, that's awesome. We have 1,000 people on campus who are using this thing, all interconnected. You see, the way to read this chart, these are not sick people. The way to read the chart is there's 2 people that they spend time with. Those 2 people spend time with 3 people. The 3 people spend time with like 20 people, and so on. And the 20 people are not yet counted in this part. These are all graph theoretic shortest path lengths. Okay. Now, if you see, it kind of goes up and down. The only reason it goes down is because this is in a university. If it was the whole city, you just keep going up. 6 degrees of separation does not mean that they should all be 6, because what we're measuring are 2 phones physically around each other. Even though there are 6 degrees of separation from who knows who, that's not what we're doing. We're like, who spends time with who? And so actually it's quite far apart. But the key takeaway is, what's the base of the exponential? This is like a math puzzle, right? I mean, this is a math problem. Like what to the power of 5 is about 181. You know, it's between 2 and 3. What I'm saying is that our app had achieved an R naught of 2. Our app had surpassed an R naught of 2 in the community. And then that just caused the number of users, the user base curve, to do this, to be like basically an exponential of about 2 or 3 to the power distance. And that's actually what I knew would happen, because the theory of random graphs says that if you start with like it says in general, if you start with like a big true graph, which is called like who actually spends time with who, and you take a random subset of the vertices where each vertex is selected with some random probability, if you do this and your original graph is like reasonable, which it is, then what ends up happening is once your subgraph has average degrees of about 2 or 3, then this happens. You get this exponential blow up. You get what's called a giant component emerging, a giant connected component. So we actually knew that as soon as the typical person using the app has on average 2 to 3 other people using the app, then they will see this giant connected thing with hundreds or thousands of people all interconnected. And then they will tell each other, hey, let's start installing it. What I'm trying to say is that we would surpass this threshold of like people actually wanting to install it because they see that it's interconnected everyone as soon as you get average degree 2 or 3. Now let's do some simple calculation. Well, if you're on a university campus, and Georgia Tech was not like MIT or Harvard. Harvard, you guys were like really strict. Georgia Tech was a little bit more lax and people were like going around. If the typical person over 2 weeks, which is what we use to generate this thing, over 2 weeks has like 20 or 30 contacts that they spend time with, well then, what fraction of them need to be using the app to have 2 or 3 of them on the system? Like 2 or 3 divided by 20 or 30. Does that sort of make sense? I'm saying like, in order for this viral explosion to take off, I need that each person out of their 20 or 30 contacts has 2 or 3 of them using the app. That is a ridiculously low 10% adoption rate. What I mean is that is a ridiculously low 10% threshold after which you start to slide down. I say slide down because I think of this as a potential. I mean, in some sense, I'm not sure if this picture makes any sense at all, but if I went and drew, and this is sort of show you how my brain works and how I think about all these things. If we have like 2 axes, which is like install %, and then somehow like potential, if you do any physics or chemistry, potential is one of the most useful tools. It's like somehow things want to go towards low potential. What Novid happens to have is it happens to have something which at 0% install, yeah, that's not great. At 10% install on a university, it gets pretty interesting. And the potential curve ends up looking something like this. What I'm saying by potential is that everything wants to go towards low potential. I'm getting towards a notion of even a Nash equilibrium. That's what I'm getting at now. It's that somehow, if you think about this kind of an app, if nobody's using it, why would you install it, right? But there's actually 2 Nash equilibria on this app. Nash equilibrium means that like this is what people are doing and nobody has any incentive to change their strategy. The 2 Nash equilibria are nobody install and everyone install. Because actually for this app, it never asks you to quarantine. We don't even care about that. Actually, we think that's bogus. Sorry, you should quarantine if the contact tracers ask you to. But we don't think that app-based quarantine is useful for multiple reasons. But somehow, we don't even bother to go and ask people to quarantine. It's just like you install this app, you'll get to have a radar. You get to see if something's coming. And if you imagine that everyone had it except you, would you want the radar to see what's coming? Well, yes, because everyone's got it already. You install it and you see like I've got like thousands of people I'm connected to relaying signals to me. It's awesome. And so that's the Novid, right? That's us. And potential is where you want to fall to a lower potential in like the physics context. But if you think about all of the other apps, everything else that existed is this. Others. And the reason is because if you think about what all of the other apps do, those are called contact tracing apps. Those are apps which tell you, hey, you've already been around somebody, you should go quarantine. Those apps do not directly help you avoid getting sick. They let you be a good person to go and help other people not get sick after you've already been exposed. And so the way that one works is that at the beginning, no one has it. The early adopters join, the altruistic people join, and it gets harder and harder and harder to convince the selfish people to join. Whereas for us, because of the fact that we have this interesting 10% point in a university setting or a school setting, after which we have this massive interconnectivity, then we start to slide down. And that's actually what we saw happen in the deployments. I'm not sure if that's the question you were asking, but this is like our goal is just to keep sliding down and to leverage the fact that if you change the sign of the slope, it's awesome. Like that's what you think of mathematically, right? We just change the sign, SIGN, and that's it.
So I think you sort of, I guess, hinted at this near the end of your talk. But I guess what sort of advice do you have for the attendees who want to make a contribution to the world in terms of a novel idea? I mean, I think many people often, when they think of, great discoveries and innovation, they think of things happening with a flash of insight. But I guess, along with how does one prepare oneself for a future situation where they could actually have a novel idea? But also, I guess, how do novel ideas actually come to be? Could you speak a little bit about that?
Yes. So if you have noticed, like somehow I actually am very attracted to novel ideas. I sort of like, that's what I care about. I also actually care about the execution. Like once I bite on something, I will just go and be like, oh, there's something novel here. Let's push it all the way. But the novel idea part, again, because you can see for some reason, I bothered to think about how to solve quadratic equations. Like, why would anyone do that? Honestly, it's like, because that's just my habit. Or this thing about finding this other way to do things. One of my habits is if I ever see something going on in the world, I always ask, is there another way to do it? And I got this actually from math competitions, because that's how I check my answers to avoid sillies. So no, seriously. So like the way I always, let me tell a lot more stories about this, right? So my entire way I approached math competitions when I was in school was I just wanted to come up with weirdo solutions for fun. Okay, I was at MOP one year, and like if you're at MOP, usually you try to get good scores, maybe not. But there are these MOP tests. I'll just tell you the story of how this works, right? So when you're at MOP, you get some tests you take every other day, and usually after the test, people are like, "Hey, how many problems did you solve? Did you solve all 3 of them? Did you solve like 2 of them? Or like, what'd you get?" I decided the second year I was there, I was not going to try to just like solve as many problems as I could, because if you just wanted to solve as many problems as you could, you might just be like, you bash it and it'll get done. Like that's no fun. Why would I waste my time bashing a problem? That's just complete waste of time. All you get is points. All right. Sorry if that's your style. I mean, it's just like, no, it's okay. I have respect for people who get points too. Actually, some people are really awesome at that. But my personal thing was like, I don't want to do that. So what I would do is after every test, like my goal was to have come up with a solution that nobody else in the camp came up with. So like after each test, we'd just like chat and people would be like, hey, how many did you get? How many did you get? I would get like 1, okay, 1 problem. But that's because I spent the whole time trying to think of like the weirdest way to do it. It's like there are these some games sometimes you're like thinking of words and can you think of the word that nobody else thinks of? I don't know if anyone's played these games, but like I really enjoyed can you do the thing that nobody else does, because it's just so ridiculous. It's like sometimes I would solve like a normal geometry problem by like applying something called Pascal's theorem 6 times. And that was before it was cool, right? Like it's just like like people did it by angle chasing and they're like, why didn't you do it the simple way? Well, because it's more fun to do something weird, right? And so I would just always do that. And also when I was studying for middle school math competitions, like my coach of my middle school math team, his style was very simple. Like he would just always ask us to explain how we did the problems. And you would get to explain something if you have a different solution than what other people have done. So it was more fun to just like keep coming up with weirdo solutions. And I've just always done this. It's like in real life too. If I go and see normal people like walking on one side of the street and most people are walking on that side of the street, I start thinking, should I walk on the other side of the street? Would there be any advantage? Sometimes the answer is yes. Most of the time the answer is no. But it's good to do this exercise. And I just am always doing this exercise with all kinds of things, which is also why like you can see the way I'm doing this talk. It's like everyone uses screen share. Yes, that's the status quo. Can I do something different? Right? And it's just like, there's this act of like thinking every single thing I do. It's like, is there a different way to do it than what the world is doing? And 99% of the time you realize the world was right. 1% of the time, you realize the world missed something. But most people don't spend their time actively like questioning, why is this? Why is this? Why is this? And so they just don't notice it.
Thank you very much. Could you talk a little bit about, mathematics is a challenging subject for a lot of people. And not just mathematics, but, the other disciplines that you mentioned, physics, computer science. I guess could you talk a little bit about your experience with learning these subjects and how do you learn?
So I actually just like learning stuff. Okay, so I'm one of these guys who, if I went to look up something on Wikipedia, I can easily get distracted and be like, hey, I wonder what that is. And you click on it. And it's like, oh, I wonder what that is. And you click on that. And after a while, you get to philosophy, right? But there's some joke that if you keep clicking on the first thing on the Wikipedia link, you get to philosophy. But in any case, it's just like, for me, I always want to get more knowledge, information, methods. I'm curious. And this is actually something that I say we because I also am an interviewer for the Hertz Foundation. Like, we're always looking for like intellectual curiosity. One thing that's sort of the difference between like doing things for points versus doing things just because you want to know, if that makes sense. So for me, like when I started to learn physics, I was at Caltech. At Caltech, back when I was there, no matter what you majored in, you had to learn quantum mechanics. It was like part of the core curriculum. Okay, I actually had a friend who was a biologist who like you had to do like five quarters, which is like okay 5/3 really if you think about academic years. But he had to do all of these like physics classes and math classes. And in the end, when he finally got done with all of those, he was like, finally I can do my biology, right? He's a neurosurgeon now. But in any case, it's just like I had to learn all these things. But if I get exposed to them, I just get curious. It's like, I wonder how that works. You know, there's all these problems in this like electricity and magnetism book. And there's like this interplay between special relativity and the interplay between E and M, electricity and magnetism. And I just got curious. So like the book has problems. You start thinking about them. There are problems that are assigned to you. I actually had a reputation for doing all the problems, whether they're assigned or not, because that's how you know which ones are the interesting ones. Like you can go and you can play with them. Of course, when I'm doing all the problems, if I see that, yeah, that's just like standard, I already know how to do it, I wouldn't finish the calculation. I'll just be like, yeah, I know I could finish it if I wanted to. But then here's something else I just don't know how to approach. So my thing was, I'm one of those guys who, even though I was a math major, if I'm taking a chemistry class, I actually want to get it all the way. Not just like one of those things which is it's a general education requirement, just like pass chemistry, if you know what I mean. My goal was like, if I'm sitting in this chemistry class and that teacher is one of these like world famous chemists, which they all are. I mean, wherever you are at university, they all are. I didn't blow it off. I'm like the guy or the lady, they know their stuff. Let's go and try to find out what they've got here. So my point is, whatever I was learning, I would actually go and try to. This was also kind of dumb in retrospect, but I was trying to get like, I don't know. I was trying to get a perfect GPA because that was like a thing of, can you really see if you understand everything? And at Caltech, there's an A+, which makes it harder to get perfect because then you have to go beyond the A. But I was just like, can I try to make sure that whatever I was doing, I actually understand every single piece of it? And today, I think that's been really useful because what I ended up needing for a lot of the work that I eventually do is just like a broad swath of scientific knowledge on which you can build new things and you can slot new things in relatively easily. So I guess the main thing is, if you can tell, math was important to me. And of course, I made sure to drive forward in math. But all of the other things I didn't think of as waste of time. And for example, one of them is called writing in English. A lot of people who are doing math absolutely detest writing or creative writing or any of those things. I spend most of my day these days like writing and communicating to convince like other people that what I'm doing should take their attention. And it's one of these things you don't normally think about, because if you're only going to innovate within your field, you might never have to interact with like some random other person who's like an undersecretary in the national government of some other country. But once you do, you realize that talking to them about graph theory is not going to get you anywhere. Like that's just like useless, right? And you need to figure out other ways that can make communication effective. So again, that's like, for me, even when I was taking English classes, it's like, go and do them well too.
So you mentioned a lot about sort of a lot of different types of math that go into the whole process of creating Novid. Would you maybe like feature a specific type of math, I guess besides graph theory, that was especially pertinent to Novid?
Yeah. So let me really briefly run through a few of these, right? So yeah, graph theory is not the only one. Probability is not the only one. At some point, what we were doing is, and we're still doing it actually, we use ultrasound to measure distances between certain devices. And you need to then be able to figure out whether or not there was another device making a certain noise. Because the way it is like each of our phones makes some noise, and it's a characteristic noise, so that if you had like 10 phones in a room, you can tell them apart. And the heart of that is something called Fourier analysis. So for example, if you get a sound signal, I'm just doing this really fast because this is HMMT audience, so I assume people know a lot of these things. But if I just draw like two axes and I'm getting a sound wave, suppose what ends up happening is at a certain point, suppose like the thing that's coming from my microphone, the signal I'm getting is like this, and then suddenly I get this. Our signal, by the way, is not a straight up sine wave, okay? But I'm just making things easier just so that you can sort of understand the foundations of Fourier analysis. So the point is, this is like over time, right? So this is an axis over time. And this thing is displacement. This is like basically the sound wave that you've gotten. And this thing, the characteristic frequency we're looking for, maybe it's something like sine. I'm making up some random numbers, 7t. For me, 7 is my random number. If it works for 7, it works for anything. So that's how I do proofs usually. I do it for 7. I look for patterns. Okay, this is actually legit. And then you go and make some variable and it works. But so suppose I have this like sine 7t, and I want to know like when it started, right? Because, oh yeah, how do we find out how far away devices are? You start making a noise, and you go and figure out how long it took for the noise to get to the other device. So the key question is, when does it start? Does that make sense? It's not like, one question is there that frequency underlying? That's easy. That's called like your spectrum analyzer. You may have noticed that sometimes if you're listening to music, you can see all these frequencies, and it's kind of cute. Like when the bass goes, you see lower frequencies. When some like really high pitched thing goes, you see high frequencies. But I don't care about which frequencies there are. I need to know when it starts. Do you see what I mean? That's a slightly different problem. How would you do that? Well, it's actually like, here's a very rudimentary way. This is actually not what we do, but we do something more sophisticated. No, actually, we do something like this. But if this was your signal, okay, that's sine 7t is the true signal. Starting somewhere. Starting at some time. And by the way, this is the measurement of a microphone. So the microphone is measuring, and suddenly it starts at some time. And we need to know like exactly when that time is, because then we'll subtract the time that the transmitter transmitted at. And now we've got a time gap, time delta. Multiply the time delta by the speed of sound, you got a distance. But now how would you do this? Well, let's call the actual signal, the received signal, is f of t, okay? Now, something that really nice that happens is if you actually went and integrated, and by the way, if f of t, let me be clear. F of t equals sine 7t, plus some noise. So some noise. What's a good noise? I guess I'll call it g. Why not? GT. This is noise. And the GT is like some random noise. Noise is not necessarily small, by the way. You could have like some really loud room, and there could be some crazy other noise. But the important thing is that this noise doesn't have that much in this special frequency. And now what you do is if you just integrated f of t against something like sine of 7t dt, and you integrate it from like 0 to some capital, let's call it L. All right, if I'm integrating it from 0 to L, interesting things happen. It turns out that when L is here, if this is L, it turns out that your integral is basically nothing. And that's from something called Fourier analysis. The reason why that's true is, I'm talking very fast because, again, this is like just giving you a glimpse of how this math works. It's because if I was integrating over like some long region, 100's a long region, that's good enough. If I do something like sine 7t, oops, I want to do the function itself. The function is actually, every function you get is actually decomposable into a sum of sines. That's called Fourier analysis, sines and cosines. But if you, for example, had a different thing, like suppose you had a frequency component with a different frequency, sine 3t, sine 7t, that's the thing that I'm always multiplying the integral by. This is interesting because if I go and take this integral, the answer is almost nothing. The reason is because there's a product to sum identity for sines, which I already forgot. I just know there's one. So what's the product of sum? What's the product of sum? There's like some, what? Is it a 1/2 that comes? Or is it a 2? It's a 1/2, I think. There's a 1/2. And then what do you get? You get like some sine. No, sine will be a cosine. I'm going to make some stuff up and see if it works. What if I subtract them? And then like cos. I'm going to try this. Is that true? It's like this or like minus or like something. Does anyone know what this is? Help me fix it. So it's the sine times sine. What is it? Did I do that right? What I did is like the 3 minus the 7, and then the other is like the 3 plus the 7. I actually don't remember. Anyone know? We got enough smart people here. Am I supposed to add them? So it's like, okay, look, let's just do it slowly. All right, so if I have cosine of A plus B minus cosine of A minus B, all right, this is how we do it. This is cos A, cos B. Now you see that all the stuff you're learning is actually useful. sine A, sine B, and then minus, okay, this is cos A, cos B, plus sine A, sine B. All right, so then when I do all of this, I do get the minus on the sines. It's right? Wow, okay, I got lucky. Anyway, it's just like it's like with a plus or the minus or the 1/2 or the 2, I don't need those because actually what matters here, look what happens. If you integrate this over long ranges, it just cancels. Is that clear to people? Because like these signs are periodic. So if I take this integral, I can make the 100 into 10 million, and I'm not going to get anything bigger. Does that make sense? The key is this is like small. This is tiny. Not growing in T, like not significantly growing in T. Okay, so I'll just stand here. So that's how we've got this. But the interesting thing is if you actually see what happens once this frequency starts, if you take this integral and it's sine 7t times sine 7t, suddenly you're picking up stuff. Does that make sense to people? Like if you have sine squared of 7t, it's actually a non-negative function all of a sudden. And if I didn't have the 3t, but I had a 7t instead, if I take this integral and I'm doing like this from 0 to like a big number, what I'll end up getting is I'll keep picking up more and more and more value. That's the key difference. The key difference is this product to something. If they were both 7, this would be cosine of 0t. Cosine of 0t actually is just 1. That's actually why this is interesting. So then what you get is it doesn't cancel away. Like these integrals right now cancel away. But what you are not getting if you have the 7t is you get something. So to give a punchline of this, if you actually take this integral of from 0 to L, and you want to know what is the integral of the signal you receive times the sine of 7t, what you end up picking up, this integral, if I was to plot the integral, the plot of the integral, it's going to be like some wiggly stuff here until you get to that point, and then it has a sudden like slope where it does this. Is this sort of clear to people what I mean? What I'm saying here is like, if I'm plotting, like this f is the signal that I'm measuring. And if I take the integral from 0 to the x coordinate of the f times this particular sine of 7t, what I actually pick up is like random wiggling. And then suddenly this like hockey stick takes off. And it takes off at roughly a constant slope. And the reason it takes off at roughly a constant slope is because of the periodicity. Because if I had like sine 7t, then like every time I finished a period of the sine 7t, I picked up some positive stuff, and then I do it again and again and again. And you can use this to figure out where it starts. Okay, this is like very rudimentary, but actually if you want to do this more properly, that's actually an entire area of like how you design radars and sonars. And along the way, we accidentally had to figure out how they make radar and sonar, how you make pulses, how you find out like a lot more sophisticated ways than what I'm just showing you. But this is all this, it's called Fourier analysis. And at that point, I was just so happy that I had paid attention in that math class, which was about Fourier analysis that I took as a sophomore, where I was like, when am I ever going to use this stuff again, right? But it was in a pure mathematics course on analysis. And I just paid attention so that when I like last year was stuck trying to figure out what's going on here, I don't have to take anything as just like, well, it is done this way because it's done this way. I was like, well, let's dig into these like integrals and the cosines and was able to understand things well enough to go and build it. Okay, that was probably longer than you were expecting, but.
I think we have probably time for just one more question. Yeah. So Professor Lowe, you've had really a wide range of experiences of participating, coaching, competition math, researching, teaching, et cetera, et cetera. What is sort of one closing thought, reflection, or piece of advice that you have for the people who are listening to you today?
My biggest piece of advice is you can spend a lot of time working on a problem. In fact, a lot of problems in the world that you work on will take you time to solve. You eventually get to choose what problems to work on because you get to choose where you work, or depending on your workplace, you might get to choose which project you work on. Or if you start your own company, then you get to choose what you do. Or if you're a professor, you just kind of choose what you work on. What I'm saying is that the choice of where to throw your time is actually valuable because it's like, if the most you could get out of that particular direction is like this, you can throw all the time at it and you'll get this. And that's explaining perhaps why as soon as I realized, my gosh, this thing could change the way humans fight disease forever, well, then the ceiling's very high now. So it's like, I'm going to throw all the time there, right? And I'm actually very careful about where I put the rest of my time. So it's one of these things where it's useful to think what question you should be working on. And a lot of the people who are watching this are like very highly capable people. And I learned this from my PhD advisor. I mean, he told me once, it's like, if you're going to work on a problem, make sure that after you're done with it, people will care that you did it. That's how you decide what research problem to work on, not the other way around, not just like, oh, I'm in front of a problem, let's just go and do it because the problem's here, right? So I think the biggest thing I want to leave people with is, if you have this ability, since all of you have this very strong technical ability, I really hope that when you decide what you want to work on, you do think about like, oh, maybe this thing could be big. Maybe this thing could have some importance. And my own history is, yes, you're hearing about this thing now, but I got here like with very small steps. And it's like, it's always one of these things where another piece is like, ideally keep working. It's like I told you after I got that, okay, this quadratic thing, it's like, okay, a lot of people will be thinking about using this for a long time. And instead of saying I'm done, I was like, now how do you top that? You know what I mean? It's like whatever you've done, you always try to say, what's the next thing that I can do? And if you just keep moving in that way, then eventually you'll get to some pretty interesting things with this combination of luck as well. So I really hope that, people who are watching this someday, maybe you'll happen to be able to contribute in some way that helps many other people as well. I definitely did not jump from like 16-year-old me to this 39-year-old me. I actually don't know how old I am. If I could subtract, I could figure it out. I don't think I'm 39, am I? What was last year? You see, the whole year disappeared. I can't be 39, I'm 38. Am I? Anyway, this is too hard. Yeah, I'm 38, whatever. But it's just like, it doesn't jump that way. What you do instead is you just kind of keep attacking and you keep attacking and keep attacking. You guys love challenge, great, keep on doing it. And I sincerely hope that someday the things that you do will leave something that helps the next generations. So thank you.
Thank you, Professor Lowe, for the incredible talk and conversation. I think you've definitely left a lot of things for us to think about as we move forward as a generation. So to all the attendees, congratulations on completing the test today. Thank you for attending this event. For more HMMT education events, please join us tomorrow for the remainder of our classes, which you can find at link.hmmt.org/catalog. So have a great rest of your night, and we hope to see you tomorrow. Thank you again, Professor Lowe.
Bye-bye.